You saw it on the thumbnail. An explosion so powerful it outshines 1 trillion suns in a single instant, lighting up the cosmos like a cosmic lighthouse. Right now, you're strapping in for an odyssey across the most extreme forces in the universe, from the secret wars inside every atom to the roaring abyss of black holes and beyond. By the end of this 10-minute chapter, you'll not only grasp how these titanic interactions operate, but you'll discover the hidden thread that weaves them all into one grand cosmic tapestry. Stick around, because later in this hour, you'll encounter a theory so unsettling it could rewrite the ultimate fate of existence itself. Yet right now, we're diving headfirst into the engine room of matter. No small talk, no wasted seconds. Imagine the heart of a massive star, millions of times heavier than our sun. Temperatures soar into millions of degrees. Pressures crush atoms flat, and protons packed side by side should repel each other like two identical magnets forced to meet North Pole against North Pole, yet they hold together, forming the nuclei of atoms, and that is thanks to the strongest force in nature, not gravity, not electromagnetism, but the strong nuclear force, a binding power so immense it leaves every other interaction in the dust. Here's the deal. The strong force glues quarks into protons and neutrons using carriers called gluons, and it only works over distances smaller than the width of a single proton. Step outside that tiny realm, and the force vanishes like a phantom, but inside it reigns supreme, about 100 times more powerful than electromagnetism, and roughly 1036 times stronger than gravity. That's gravity compared to a thunderclap, only the thunderclap is the strong force, and gravity is a faint whisper. Without this binding energy, atomic nuclei would fly apart, stars would never ignite, and the universe would be a featureless fog of solitary particles. No chemistry, no planets, no life. Just lonely protons and electrons drifting in an empty void. Think of it like this. You take an unbreakable rubber band and stretch it. As you pull, the band doesn't give way. Instead, it thickens and resists harder with every inch you pull. Now replace that rubber band with quarks and gluons, and the resistance skyrockets. Try to rip a quark from its proton home, and the more energy you pour in, the stronger the bond grows. Any extra energy just spawns new quark-antiquark pairs, sealing the chain forever. It's a cosmic catch-22. The harder you fight to break free, the tighter you're held. Now pause and consider why this matters beyond theoretical physics. In the blazing cores of stars, hydrogen nuclei fuse into helium under titanic pressures, releasing the heat and light that fuels galaxies. The rate of fusion, the lifetime of stars, the very emergence of elements heavier than hydrogen, all hinge on the strength of that nuclear glue. If the force were a hair weaker, stars would burn out in seconds, never allowing planets or life to form. If it were a hair stronger, fusion would run away like a bomb, instantly obliterating stellar furnaces. That razor's edge balance crafted a universe where carbon, oxygen, iron, and every atom in your body came to be. Rewind 14 billion years to the first minutes after the Big Bang. Temperatures were so extreme that quarks and gluons roamed free in a primordial plasma, unbound by the confines of protons. As the cosmos cooled and expanded, those quarks and gluons locked together into protons and neutrons, then fused into hydrogen and helium nuclei in a fleeting moment called Big Bang nucleosynthesis. This cosmic alchemy seeded the universe with the raw ingredients for stars, galaxies, and eventually life itself. What began as a seething quark sea set the stage for the galaxies we see today. To understand this in a lab, physicists slam heavy ions together in particle accelerators at near-light speed. The collision briefly recreates that primordial plasma, a fireball where quarks and gluons abandon confinement before cooling reforms them into new particles. These experiments test our deepest theories of quantum chromodynamics, the rules governing the strong strong force, and reveal how matter behaves under conditions we can never achieve on Earth naturally. They're our window into the universe's origin story, played out on a microscopic stage. But don't drift off yet, because the same strong force mechanisms power the universe's brightest fireworks, gamma-ray bursts. These cosmic lighthouses are born when the most massive stars exhaust their nuclear fuel. In a final violent struggle, gravity wins and the core collapses in on itself faster than a blink. The implosion rebounds into a supersonic shockwave that tears the star apart, forging heavy elements and blasting them into space. In some cases, twin jets of particles burst through the dying star's outer layers at over 99.99% of light speed, releasing more energy in a few seconds than our sun emits in its entire 10 billion-year lifespan. Picture it, a beam of pure gamma-ray energy, so focused and intense that if you could see it, it would outshine the full moon from 2 billion light-years away. In October of last year, a record-setting burst lit up detectors across every satellite in orbit and even left subtle signatures in Earth's upper atmosphere. It forced scientists to rethink how jets punch through collapsing stars and how their magnetic fields focus that raw power into narrow beams that can travel across the cosmos almost unimpeded. Here's your first retention hook. In just a few minutes, I'll break down why some gamma-ray bursts flash for mere milliseconds, while others stretch on for minutes, and how subtle differences in a star's spin and magnetic field determine the burst's duration and brightness. Trust me, that comparison will blow your mind. But first, let's unpack the physics of those jets. As the core collapses, matter falling into the newborn black hole spins up, forming a superheated accretion disk. Magnetic fields twisted by that maelstrom act like cosmic rails, channeling the infalling gas into twin streams launched from the poles. Those streams slice through the star's envelope, like bullets carving through fog, until they burst free into the interstellar medium. As the jet plows ahead, shock fronts accelerate particles to relativistic speeds, and the result is a gamma-ray beacon that can outshine entire galaxies. On Earth, scientists simulate scaled-down versions of these jets using ultra-powerful lasers focused on tiny targets. The experiments generate mini shockwaves and magnetic fields that mimic those in dying stars, offering insights into jet formation and stability. By studying these laboratory astrophysics setups, researchers improve their models of gamma-ray bursts and the extreme physics at play, bridging the gap between data from space telescopes and fundamental quantum theory. So far, we've mapped the path from quark confinement to the brightest explosions in existence. Up next, we'll zoom out one more time to confront the ultimate cosmic vacuums, black holes that devour light itself. We'll journey to the hearts of galaxies, where supermassive black holes lie in wait, millions to billions of times the mass of our sun. These gravity wells sculpt galaxies, power quasars that outshine billions of stars, and send jets of plasma screaming through intergalactic space. And here's your second retention hook. Later, you'll witness a cosmic tango between two supermassive black holes spiraling together in a cataclysmic merger. That cosmic collision sends ripples through space-time itself, gravitational waves you can almost hear if you know how to listen. Those waves stretch and squeeze space as they pass, and Earth-based detectors pick them up as faint whispers from a billion light-years away. It's a sound straight out of science fiction, yet it's real, and we'll dissect it in a bit. Before we get there, let all this sink in. The same strong nuclear force that holds quarks inside protons also orchestrates the collapse of stars, the birth of black holes, and the most powerful light shows in the universe. If you thought physics was just chalkboards and equations, you're about to see it's the grandest story ever told, one where the smallest interactions dictate the biggest spectacles. In the next chapter, prepare to witness how gravity and light collide in the cosmic maelstrom of black holes, and learn why nothing in the universe escapes their hungry grasp. In a moment, we left off on the brink of the most intense fireworks in the universe, gamma-ray bursts, and now it's time to dive deeper into their mechanics, their origins, and the breathtaking variety that keeps astronomers glued to their monitors at 3 in the morning. Picture the collapse of a massive star's core. As nuclear fuel runs out, pressure plummets, and gravity drags matter inward at rates faster than your eyes can blink. Within milliseconds, an entire stellar heart compresses to nuclear densities. The inward rush halts abruptly when nucleons collide at the center, rebounding in a supersonic shockwave that tears the star's outer layers to shreds, fusing heavy elements that seed the cosmos. This dramatic rebound underlies a core collapse supernova, but in some stars, that initial blast is only the opening act. In the most extreme collapses, where rotation, magnetic fields, and stellar structure align just so, a pair of narrow channels open along the rotational poles, matter funnels into the newborn black hole with such ferocity that magnetic field lines twist like rubber bands until they snap, driving twin jets of plasma outwards at velocities exceeding 99% of light speed. These are the gamma-ray bursts. They blaze brighter than 1,000,000,000,000 suns for a few fleeting seconds to minutes, their high-energy photons traversing the universe until our satellites catch them in a brief, dazzling flash. Because of this brevity, astronomers classify GRBs into two main families: long bursts lasting more than 2 seconds, usually from massive star collapses, and short bursts under 2 seconds, thought to originate in neutron star, or neutron star black hole mergers. Short GRBs, though briefer, pack a similar punch. When two neutron stars spiral together over millions of years, they lose orbital energy via gravitational waves, accelerating until they collide. The resulting merger briefly forms a hypermassive neutron star or collapses directly into a black hole. In either case, tidal disruption ejects neutron-rich material that rapidly undergoes nuclear reactions, producing heavy elements like gold and platinum. Simultaneously, magnetic fields amplify and launch jets, giving rise to a brief gamma-ray flash. Last year's event that matched up with both gravitational wave detectors and gamma-ray observatories catapulted multi-messenger astronomy into a new era. Scientists witnessed, in real time, the colliding neutron stars and mapped the kilonova aftermath, the glow from radioactive decay of freshly formed elements. Both classes of GRBs exhibit what astronomers call afterglows, fading emissions at X-ray, optical, and radio wavelengths that can last days to months. By studying afterglows, researchers track how jets interact with surrounding interstellar gas, measuring jet opening angles, estimating total energies, and even pinpointing host galaxies billions of light-years away. In one remarkable case, an afterglow persisted for months and revealed signs of a structured jet, where the energy distribution varied with angle. Such observations inform theoretical models, but they also hint at tantalizing possibilities. Under the right circumstances, GRB jets could impart enough momentum to trigger star formation in neighboring clouds or sculpt galactic environments on vast scales. But gamma-ray bursts are only one piece of cosmic drama. Let's shift the lens to supernovae themselves, those titanic explosions so familiar to backyard astronomers that some can briefly outshine entire host galaxies. Core collapse supernovae, as we've described, mark the violent death of massive stars, leaving behind neutron stars or black holes. However, another category, type Ia supernovae, arises in binary systems where a white dwarf star siphons matter from a companion. Once the white dwarf reaches a critical mass, a runaway thermonuclear fusion ignites, burning carbon and oxygen into heavier elements in a flash so bright it can light up a galaxy for weeks. Type Ia events play a crucial role in measuring cosmic distances because their peak luminosity is remarkably uniform, making them standard candles that helped reveal the universe's accelerated expansion. Beyond these, theorists predict supernovae born from pair instability in extremely massive stars, where energetic photons transform into electron-positron pairs, softening internal pressure. The star partially collapses and then violently re-expands, disrupting itself entirely without leaving a compact remnant. These pair instability supernovae can synthesize enormous quantities of heavy elements and stand out for their brightness and duration. Astronomers searching the early universe hope to catch glimpses of these exotic explosions, which may have enriched the intergalactic medium before the first galaxies took shape. Equally riveting are hypernovae, events more energetic than typical core collapse, often linked to long GRBs. In hypernovae, rotational energy and magnetic fields combine in a magneto-rotational collapse, that amplifies explosion energy by orders of magnitude. The jets carve through the star's envelope with focused precision, leaving elongated remnants that emit strong radio waves for centuries. These explosions offer clues to how the most massive stars end their lives and contribute to the cosmic supply of heavy elements, critical for planet formation and the chemistry of life. From supernova heavens, we move to black hole hellholes. When a star's core collapses beyond the neutron star stage, nothing can halt the collapse. No nuclear pressure, no quantum degeneracy. An event horizon forms, and a black hole is born. On the stellar mass scale, these holes range from a few times the sun's mass up to tens of solar masses. We detect them indirectly as X-ray binaries, where a companion star donates material that forms an accretion disk around the black hole. Friction heats the disk to millions of degrees, emitting X-rays that satellites pick up. By measuring X-ray luminosity and orbital parameters, astronomers estimate black hole masses, spins, and accretion rates. These measurements test general relativity in its most extreme environment. But the real cosmic titans are the supermassive black holes at galactic centers. Their masses span millions to billions of solar masses. The Milky Way's own Sagittarius A weighs in at 4 million solar masses, quietly accreting at a low rate, until occasionally flaring up in infrared and X-ray light from infalling gas. In other galaxies, so-called active galactic nuclei blaze with vast power as accretion disks funnel material at near Eddington rates. These AGN can outshine their entire host galaxies, driving winds and jets that regulate star formation. The most extreme of these are quasars, whose luminosities can exceed 100 trillion suns. Light from quasars, dating to when the universe was under 1 billion years old, raises a puzzle. How did these black holes grow so large so quickly? The rapid growth likely involves direct collapse of massive gas clouds, super Eddington accretion episodes, or frequent mergers with other black holes. Speaking of mergers, in 2015, gravitational wave observatories made history by detecting ripples from 2 colliding stellar mass black holes. Since then, dozens of mergers have been catalogued, revealing a surprising population of heavyweight black holes, some tipping the scales at 50 solar masses or more. Each merger tells a story about stellar evolution, black hole formation, and the environments that breed these monsters. In parallel, detectors are edging towards sensitivity for supermassive black hole mergers. One day, observatories dedicated to low-frequency gravitational waves will capture the colossal union of galaxy-scale behemoths, accompanied by electromagnetic fireworks in quasars and jets. Meanwhile, high-resolution imaging like the Event Horizon Telescope has given us the first silhouette of a black hole's shadow in the galaxy M87. That landmark image confirmed predictions of general relativity, showing a dark, circular region where light is trapped and a bright ring of glowing plasma. Imaging efforts continue to refine our view, aiming to capture the dynamic behavior of accretion and jets on event horizon scales. Throughout these chapters, one thread remains constant: the same fundamental forces we explored in atoms, gravity, electromagnetism, and the strong nuclear force, all interweave to produce cosmic phenomena of mind-boggling scale and beauty. When a neutron star merger sparks a kilonova, when a core collapse supernova reshapes a galaxy, when a quasar blasts a jet across intergalactic space, it is the interplay of these forces that governs every detail. In a little while, we'll venture even further, exploring the eerie domain of neutron stars where matter reaches densities unimaginable on Earth, and then dive into the ultimate frontier of physics, dark energy, and the expansion of space itself. But for now, reflect on the saga we've covered, from quark confinement to gamma-ray bursts, from supernova cores to black hole mergers and quasars. Keep your eyes on the sky, because up next we'll uncover how the densest objects in the universe challenge our understanding of matter, magnetic fields, and the laws of nature. Now we leave the realm of black hole mergers and step into a universe so dense that a single teaspoon of its matter outweighs Mount Everest. Neutron stars are the relics of massive stellar deaths, city-sized spheres where gravity crushes protons and electrons together, forcing them to merge into neutrons. Imagine packing a sun's worth of mass into a sphere barely 20 kilometers across. The result is a pressure so extreme that atoms as we know them collapse, and the fabric of matter enters an entirely new phase. These stellar corpses spin at astonishing speeds, some rotating hundreds of times per second. Their beams of radiation sweep across space like lighthouses, delivering pulse after pulse with clockwork precision. Astronomers detect these pulses as rhythmic flashes, signals more regular than the most accurate atomic clocks on Earth. Researchers use pulsar timing arrays to study gravitational waves, measure interstellar medium properties, and even test general relativity under conditions impossible to replicate in laboratories. But a subset of neutron stars takes extremity to another level: magnetars. Their magnetic fields reach a quadrillion times the strength of Earth's field, so intense that they can twist the vacuum of space itself into a birefringent lens, affecting how light travels. If you could stand anywhere near a magnetar without being vaporized instantly, its magnetic grip would tear electrons from atoms and shred molecules at a distance of thousands of kilometers. Giant flares from magnetars release more energy in a fraction of a second than our sun emits in 100,000 years. One such flare, observed just a few years ago, momentarily altered Earth's ionosphere despite occurring tens of thousands of light years away. These cosmic dynamos challenge our understanding of magnetic field generation and decay. Scientists believe that field amplification occurs during the first seconds after a neutron star's birth, when turbulent flows and differential rotation twist seed fields into monstrous strengths. Over time, magnetars slowly bleed their energy away through magnetic reconnection events, starquakes, and particle winds. The result is a fireworks show of X-ray and gamma-ray bursts that can be detected across the galaxy, and sometimes provoke amateur astronomers to gaze at the night sky in wonder. Now here's your retention hook. In just a few minutes, you'll hear how the same processes that power magnetars might also jumpstart magnetic explosions in the most massive stars, leading to an ultra-rare class of explosions even more powerful than gamma-ray bursts. Trust me, that chapter will stretch your imagination further than anything you've heard so far. Venturing beyond known astrophysical objects, theorists speculate about one-dimensional defects in space-time called cosmic superstrings. These hypothetical filaments may have formed during phase transitions in the early universe, spanning distances comparable to galaxy clusters while measuring less than a proton in width. If two superstrings intersect, they could generate gravitational waves with unique signatures, ripples in the fabric of the universe, unlike those from black hole mergers. Detecting these signals would open a door to physics beyond the standard model and potentially confirm the existence of extra dimensions. Though superstrings remain speculative, upcoming observatories with heightened sensitivity at low frequencies could one day hear their faint chorus across cosmic time. Before that day comes, another rare spectacle awaits exploration: magneto-rotational supernovae. In the most massive stars, rapid rotation and intense internal magnetic fields conspire at core collapse to unleash explosions 100 times more energetic than typical supernova. As the core implodes, magnetic field lines frozen into the stellar plasma amplify like twisted rubber bands, reaching strengths where magnetic pressure rivals nuclear forces. When these lines realign or reconnect, they act like colossal dynamite, launching jets of magnetized plasma at near-light speed. These jets bore through the dying star's envelope, carving narrow tunnels of destruction and seeding the cosmos with heavy elements forged under extreme conditions. Such hyper-energetic explosions present unique observational signatures: higher peak luminosities, broader spectral lines, and extended light curves that persist for weeks. In a handful of recent observations, astronomers have captured candidates for these magneto-rotational events, explosions so bright they outshine entire galaxies for months, leaving behind remnants with elongated morphologies and powerful radio nebulae. By studying them, we learn not only about the final acts of the universe's most massive stars, but also how magnetic fields and rotation shape the diversity of cosmic fireworks. Next, we climb even higher in scale to witness the grandest collisions of all: galaxy clusters smashing into one another. Galaxy clusters are the universe's largest gravitationally bound structures, each containing thousands of galaxies, hot plasma, and vast reservoirs of dark matter. When two clusters collide, their galaxy members mostly pass by each other unharmed, but the intergalactic gas clouds collide violently, creating shock waves hotter than hundreds of millions of degrees. These shocks compress and heat plasma, producing spectacular X-ray emissions and radio halos that span millions of light-years. One of the most dramatic collisions observed is the bullet cluster, where the separation of gas and dark matter during the crash provided a compelling argument for dark matter's existence. Radio telescopes have since uncovered colossal radio relics, arcs of synchrotron emission marking the location of shock fronts traveling at several thousand kilometers per second. Observing these phenomena reveals how magnetic fields thread the cosmic web, accelerate particles to relativistic speeds, and influence the large-scale structure of the universe. Speaking of dark matter, another frontier emerges in the possibility of dark matter particle annihilation. If certain dark matter candidates are their own antiparticles, they could annihilate upon collision, converting mass into energy according to Einstein's famous equation. The resulting gamma-ray photons and neutrinos might be detectable from regions of high dark matter density, such as the centers of galaxies or galaxy clusters. In recent years, telescopes like Fermi-LAT and ground-based Cherenkov arrays have searched for excess gamma-ray emission in dwarf galaxies and the galactic center, aiming to catch the faint whispers of dark matter's self-destructive dance. Although definitive signals remain elusive, tantalizing hints spur continued investigation. One strange gamma-ray line detected near the galactic center sparked debates for years before being reinterpreted, yet the search continues with ever-improving instruments. Neutrino observatories such as IceCube at the South Pole complement these efforts by scanning the heavens for high-energy neutrinos that could arrive alongside photons from dark matter annihilation or cosmic ray interactions. Each non-detection narrows the field of viable theories, guiding physicists toward a deeper understanding of the universe's hidden mass. At this point, you've traveled from the atomic nucleus to the scales of galaxy clusters, encountering objects and phenomena that stretch physics to its limits. Yet we still have chapters to explore: cosmic inflation, dark energy, and the ultimate fate of the universe. But before we dive into those mysteries, pause to appreciate the tapestry we've woven: quarks bound by gluons, neutron stars spinning like cosmic turbines, magnetars tearing atoms apart, jets carving through dying stars, superstrings whispering through space-time, hypernovae exploding under magnetic pressure, and clusters colliding in a ballet of plasma and dark matter. In our next segment, we'll venture into the earliest moments of existence, exploring how a quantum field called the inflaton drove an exponential expansion that smoothed out the universe and planted the seeds of galaxies. Then we'll follow the trail to dark energy, the invisible force picking up pace and threatening a final Big Rip scenario. And finally, we'll confront the most unsettling hypothesis of all: vacuum decay, where the universe's fabric could itself unravel in an instant. But for now, let the scale of what we've covered sink in. Remember the script so far: from the strongest force that holds quarks to the largest crashes that shape the cosmic web, a single narrative binds these extremes together. Up next, the story turns to the origin of the universe's structure and the unseen energies accelerating its fate. Don't go anywhere. Our journey into the heart of reality continues. In the earliest instance after the universe's birth, reality itself underwent an unimaginable transformation. Imagine space expanding faster than the speed of light. Yes, faster than light, stretching every tiny region into a cosmic orchard in the blink of an eye. This is cosmic inflation, the runaway growth driven by a quantum field we call the inflaton. Within a fraction of a second, the universe ballooned by a factor beyond human comprehension, smoothing out any wrinkles and seeding the density ripples that would later grow into galaxies, stars, and planets. Today, instruments scanning the cosmic microwave background reveal those primordial fluctuations, frozen like footprints in the afterglow of creation. Inflation solved mysteries that puzzled astronomers for decades. Why the universe appears so uniform in temperature in all directions, why the geometry of space is nearly flat, and why we don't see exotic relics like magnetic monopoles. The key lies in that mind-bending expansion, which stretched quantum jitters to cosmic scales. Tiny variations in the inflaton field translated into regions of slightly higher or lower density. Over billions of years, gravity amplified those differences. Some patches pulled in more matter, forming galaxy clusters. Others remained emptier, becoming the vast cosmic voids that give the universe its sponge-like structure. But what powered inflation itself? The inflaton field carried enormous energy density, acting like a seed of new space that never ran out. As space stretched, more field energy filled the vacuum, fueling further expansion, an engine with no off switch. When inflation finally ended, the inflaton decayed into the particles and radiation we know today, reheating the cosmos and kickstarting the familiar hot Big Bang. This dramatic transition from inflationary growth to particle soup marked the universe's first heartbeat. Yet cosmic inflation is only half the story. Fast forward to much later epochs, when galaxies had formed and stars were weaving heavy elements into planets and life. Observations of distant stellar explosions, type Ia supernovae, revealed an astonishing truth. Galaxies are not merely drifting apart. Their separation is accelerating. Something unseen, something that works against gravity's pull, is driving the cosmos to expand at an ever-increasing pace. Scientists call this dark energy, and it makes up nearly 70% of all the energy in the universe. Think of the universe as the surface of a balloon being inflated. As you blow air into it, every point on the balloon's skin moves away from every other point, not because the points themselves are racing, but because the space between them is growing. Dark energy behaves like that invisible breath, pumping into the fabric of space and stretching it ever faster. Despite decades of research, its nature remains elusive. Is it a cosmological constant, Einstein's greatest blunder, a property of empty space itself? Or is it a dynamic field that evolves over time, perhaps hinting at new physics beyond our current theories? Whatever the answer, dark energy's impact is profound. In the past, gravity held sway. Galaxies drew together, forming clusters and superclusters. Now, dark energy dominates, pushing galaxies apart into isolation. In the not-so-distant cosmic future, galaxy clusters outside our local neighborhood will recede so far that they disappear from view, leaving our local group as an island of stars in an ever-expanding ocean. Planets, suns, and clusters that we see today may become unreachable memories, slipping beyond the horizon of observability. And yet, dark energy may hold an even darker secret. Extrapolate its constant acceleration far enough, and every bound structure could eventually be torn apart. First galaxy clusters, then individual galaxies, then solar systems, then planets, and finally atoms themselves. This hypothetical fate is known as the Big Rip. Picture an unrelenting tide that finally erodes the very bonds holding matter together. Atoms stretch, electrons detach, nuclei dissolve, until nothing remains but a void expanding at breakneck speed. But among the most unsettling ideas in modern cosmology is the possibility that our universe sits in a metastable vacuum, a false vacuum. Quantum fields like the Higgs field determine particle masses and interactions. Right now, the Higgs may be perched on a cosmic hill, stable enough for now, but not sitting at the lowest possible energy. If a quantum fluctuation triggers a drop to the true vacuum, a bubble of true vacuum could nucleate and expand at light speed, instantly annihilating everything in its path. Inside that bubble, the laws of physics would change. Particles might have different masses, forces could behave differently, and atoms as we know them would be impossible. This concept, vacuum decay, is not just science fiction. Calculations suggest our current vacuum could indeed be metastable, with an astronomically low but non-zero probability of decay at any moment. If triggered by a high-energy cosmic ray or a collision in a particle accelerator, the bubble would race outward, leaving no warning and no escape. The thought is chilling, the ultimate reset of reality, erasing the cosmos in an instant. Before you dismiss this as far-fetched doom, consider that quantum mechanics makes even the most improbable events possible over sufficient timescales. Over trillions of years, metastability guarantees eventual decay. What would that look like to a hypothetical observer? Nothing. Light cannot escape the bubble's edge, and it expands at light speed. There would be no signal, no roar, just sudden non-existence. But let's return to the present. These dramatic scenarios, cosmic inflation, accelerating expansion, Big Rip and vacuum decay form a bleak sequence of cosmic events driven by the same fundamental rules we explored earlier. The strong force binds nuclei, fueling stars and gamma-ray bursts. Gravity pulls matter together, forging galaxies and black holes. Now dark energy pushes all apart, and quantum fields may harbor the seeds of everything's end. It's a cosmic tug-of-war writ large across space and time. In a moment, we'll tie these threads together. We'll revisit the explosion that outshone 1 trillion suns, the jets carving through dying stars, the lighthouses of neutron stars, the behemoth black holes powering quasars, and the invisible hand accelerating the universe. Finally, we'll unveil how these phenomena interconnect, revealing a grand narrative of creation, transformation, and potential destruction. You'll see how the same equations that describe quark interactions in atom smashers also govern the universe's ultimate fate. Don't go anywhere, because in our final chapter, we confront the ultimate questions. Is the cosmos eternal, or will it meet a violent end? What does tomorrow hold for stars, galaxies, and life itself? And crucially, what does this cosmic story say about our place in the grand tapestry of existence? Stay tuned. You're about to witness the finale that unites the wildest extremes of nature into one breathtaking vision. We've journeyed from the bonds that lock quarks inside protons to the explosions that outshine entire galaxies, from the lighthouses of spinning neutron stars to the hungry maws of black holes, and from the birth pangs of cosmic inflation through the invisible push of dark energy to the unsettling specter of vacuum decay. All of these extremes, though they span scales inconceivable to everyday life, share the same underlying tapestry of physics, forces interacting, balancing, and sometimes colliding in ways that shape the cosmos from the tiniest subatomic realms to the grandest galaxies. Now, as we draw this chapter to a close, let's pull back and see how each thread we've examined weaves into the bigger picture. At the smallest scales, the strong nuclear force holds quarks through gluon exchange, creating the protons and neutrons that make up every atom. That binding energy governs how stars fuse hydrogen into helium and heavier elements, fueling the furnaces that light the universe. When those stellar furnaces exhaust their fuel, gravity takes over, driving cores to collapse into supernovae that forge the periodic table's heaviest atoms. In rare cases, the collapse channels energy into narrow jets, producing gamma-ray bursts so intense they momentarily become the brightest objects in the sky. Some stars collapse into neutron stars, city-sized spheres where protons and electrons merge into neutrons under pressures beyond human imagination, spinning like cosmic turbines and emitting pulses with atomic clock precision. A fraction of these become magnetars, whose magnetic fields could rip electrons from atoms at hundreds of kilometers away if you dared to stand nearby. When two neutron stars merge, they not only unleash gravitational waves but also create kilonovae that forge precious metals like gold and platinum, enriching the interstellar medium with the building blocks of planets and life. On larger stages, black holes born of stellar deaths grow through accretion and mergers into supermassive giants at galaxy centers, powering quasars that outshine billions of stars and sculpting galactic evolution with jets and winds. Those colossi sometimes collide in multi-million-year dances that generate gravitational waves detectable here on Earth, allowing us to hear the universe's epic choruses. Even grander, collisions of galaxy clusters slam superheated plasma into colossal shock waves, painting the cosmos in X-ray and radio halos, while dark matter's hidden filaments guide the flow of galaxies like ghosts shaping the visible. Then there's inflation, a split-second growth spurt that expanded the infant universe faster than light, ironing out irregularities and planting tiny quantum ripples that later blossomed into cosmic structure. In the cosmos's middle age, observations of distant supernovae revealed that expansion not only continues but accelerates, driven by dark energy, an entity still mysterious but dominating 70% of cosmic energy density. Extrapolate that acceleration into the future, and you face the Big Rip, where space expands so quickly that bound systems unravel, planets detach from stars, and even atoms could stretch apart. Finally, quantum field theory hints at a more chilling finale. Our vacuum might be metastable, perched on a false energy plateau precariously above the true vacuum. A single quantum fluctuation or high-energy event could trigger a transition to that lower energy state, spawning a bubble of destruction expanding at light speed and rewriting physics from the inside out. These narratives, though they sound like science fiction, emerge from equations tested in colliders and telescopes, from painstaking observations of faint afterglows to the ripples in space-time recorded by gravitational wave detectors. They remind us that the universe is not a static backdrop, but a dynamic arena where forces vie and evolve across 20 orders of magnitude in scale. The same mathematics that describes quark confinement also predicts how cosmic strings might ripple through space-time, or how vacuum decay could unmake existence itself. If you step outside under a clear night sky, you're witnessing the aftermath of these grand events. The atoms in your body were forged in ancient stars. The gold in your jewelry likely originated in neutron star mergers. The rarest elements trace back to hypernovae or pair instability explosions. And on the largest scales, the expansion of the cosmos shapes the destiny of every galaxy and cluster around us. Here's one last hook before we close. Near the end, I'll reveal a simple calculation that ties together the energies of quark binding, supernova explosions, black hole accretion, and vacuum decay, showing that they all fall along a continuous curve of cosmic power. You'll see how a single logarithmic plot can map the universe's extremes on one axis, from femtometer forces to gigaparsec expansions, and how that plot hints at hidden symmetries yet to be discovered. But first, take a moment to reflect on what we've covered. We began with the promise of an explosion more powerful than a trillion suns, and we delivered not just that single flash, but an entire spectrum of cosmic phenomena. We saw how quantum forces sculpt the building blocks of matter, and how gravity and dark energy drive the universe's epic saga. We witnessed creation and potential destruction on scales from the subatomic to the infinite. Now, close your eyes and imagine the universe as a grand symphony. Each force, strong nuclear, electromagnetic, gravitational, and the mysterious dark energy, plays its part. Quarks dance to the rhythm of gluons. Electrons orbit nuclei in an electromagnetic ballet. Stars pulse and collapse under gravity's direction, and space itself rhythmically expands under the baton of dark energy. Together, they compose the melody of existence, flowing from the first note of inflation to the potential final chord of vacuum decay. I promised you a secret calculation tying these energies together. Picture a logarithmic chart with energy on the vertical axis and physical scale on the horizontal. On the left, you plot the binding energy per nucleon, reaching a few MeV at femtometer scales. A little to the right, you see supernova energies of 1044 joules. Further, jets from gamma-ray bursts push into 1047 joules per steradian. Supermassive black hole accretion disks peak around 1054 ergs. Dark energy's density multiplied by the volume of the observable universe yields a comparable figure, and vacuum decay would release effectively infinite energy per volume, suggesting a divergence at cosmic scales. This unbroken chain illustrates that nature's extremes aren't random. They follow a continuous hierarchy governed by fundamental constants and symmetry principles. What does this mean for us as inhabitants of a tiny planet? It means that every atom in our being participates in this cosmic symphony. It means the forces that bind your DNA also set the orbits of planets and the expansion of the universe. It means that our understanding of the cosmos emerges from recognizing unity in diversity, patterns repeating from quark fields fields to galaxy clusters. Now it's your turn to join the dialogue. Which of these forces stunned you the most? Was it the idea that a teaspoon of neutron star matter outweighs mountains, or that space itself might tear apart in a big rip? Maybe the thought of vacuum decay sent a chill down your spine. Whatever it is, share your reaction below and challenge someone you know to watch this video. Ask them, could you have guessed the same force shapes quarks and black holes? Before you go, here's a final provocation. 90% of people never stop to think that the atoms in their bodies were forged in cosmic cataclysms, or that the bonds holding them together rival the force of 1,000 suns. Are you going to be one of them, or will you dig deeper, question more, and keep exploring? If you're ready to take that step, hit that subscribe button, ring the bell for more cosmic deep dives, and let's continue this journey together. The universe is stranger, more beautiful, and more interconnected than fiction, and we've only scratched its surface. Let's keep listening to the grand symphony of existence. We've traveled an extraordinary distance together, from the invisible prisons holding quarks within protons to the expanding edge of the observable universe, from femtometer scales where the strong force reigns supreme to cosmic horizons where dark energy drives galaxies apart. Now, in this final chapter, we'll tie every thread into one unified vision and reveal the profound connections that bind these extremes into a single cosmic narrative. You've been promised a deeper understanding of how these forces interconnect, and the time has come to deliver that revelation. Let's return to the explosion that started our journey. An outburst more powerful than 1,000,000,000,000 suns, a gamma ray burst tearing across the cosmos from a dying star billions of light years away. That single flash encapsulates every principle we've explored. The star that collapsed was built from hydrogen fused in earlier stellar generations, hydrogen assembled from protons bound by gluons in the first moments after the Big Bang. Those protons formed nuclei through the strong nuclear force, survived cosmic inflation stretching of space, and eventually gathered under gravity's patient hand into clouds that collapsed into stars. For millions of years, nuclear fusion in that star's core resisted gravity's squeeze. Electromagnetic forces kept electrons orbiting nuclei, creating the chemistry that shaped the star's structure. When fusion fuel ran out, gravity won the ancient struggle, compressing the core until protons and electrons merged into neutrons, creating matter so dense that the laws of physics themselves twisted into exotic forms. At the moment of collapse, magnetic fields amplified by rotation-channeled energy into narrow jets that punched through the star's envelope, releasing gamma rays detectable across the universe. That gamma ray burst, then raced through expanding space, stretching in wavelength as dark energy drove cosmic acceleration. By the time those photons reached our telescopes, they carried encoded information about the star's mass, its rotation, the density of surrounding gas, and even the expansion rate of the universe itself. One event, spanning scales from quark interactions to cosmic expansion, tells the entire story of matter, energy, space, and time. Consider another connection: neutron star mergers that forge heavy elements through rapid neutron capture. The same strong force that confines quarks determines nuclear reaction rates, dictating which isotopes form in those cataclysmic collisions. The gravitational waves emitted during the merger stretch and compress space-time, ripples governed by Einstein's equations linking matter, energy, and geometry. Meanwhile, the kilonova's glow, powered by radioactive decay, spreads newly minted gold, platinum, and uranium into interstellar clouds that will someday condense into planets. Every link in this chain connects fundamental forces operating at different scales, yet all obey the same underlying principles. Black holes provide another striking example. At their event horizons, gravity warps space-time so severely that not even light can escape. Yet the energy powering quasars, those brilliant beacons outshining entire galaxies, originates from electromagnetic interactions in accretion disks where gas particles collide, heat up, and radiate. Magnetic fields threading those disks, amplified by differential rotation, launch relativistic jets through mechanisms that mirror, at galactic scales, the same physics driving smaller jets from collapsing stars. The equations governing jet collimation and particle acceleration apply whether you're modeling a stellar gamma ray burst or a supermassive black hole quasar, now turned to cosmic inflation. That exponential expansion smoothed the universe and planted quantum fluctuations that grew into galaxies. Those fluctuations arose from quantum field theory, the same framework describing gluon exchanges in protons. Just as gluons mediate the strong force through virtual particle exchanges, the inflaton field drove expansion through its potential energy. When inflation ended, the inflaton decayed into ordinary particles, reheating the cosmos in a process analogous to how excited atomic states release photons. The mathematics bridging quantum fields at femtometer scales and cosmic fields spanning billions of light-years reveals a deep unity in nature's design. Dark energy, the mysterious force accelerating expansion, poses one of cosmology's greatest puzzles. Yet hints of its nature may lie in the quantum vacuum itself. Quantum mechanics predicts that empty space seethes with virtual particle pairs constantly appearing and vanishing. Summing the energy of these fluctuations naively gives an absurdly large vacuum energy, orders of magnitude too high compared to observations. Resolving this cosmological constant problem likely requires new physics, perhaps supersymmetry or extra dimensions, theories that also aim to unify the strong, weak, electromagnetic, and gravitational forces into one coherent framework. Some theorists propose that dark energy is not constant but evolves over time as a quintessence field, dynamically adjusting the expansion rate. If true, future observations might catch subtle changes in cosmic acceleration, offering clues about physics beyond the standard model. Others speculate that dark energy signals a breakdown of general relativity at cosmological scales, necessitating modifications that could also explain galaxy rotation curves attributed to dark matter. Either way, understanding dark energy will likely revolutionize our grasp of gravity, quantum fields, and the universe's fate. Then there's vacuum decay, the ultimate doomsday scenario. If the Higgs field sits in a metastable false vacuum, a quantum tunneling event could trigger a phase transition to the true vacuum, releasing energy that rewrites the laws of physics. Calculations show that cosmic ray collisions or black hole evaporation could seed such a transition, though the probability remains minuscule over human timescales. Yet over trillions of years, even infinitesimal odds become certainties. Should vacuum decay occur, a bubble of true vacuum would expand at light speed, annihilating everything in its path without warning. No signal, no escape, just instant obliteration and the birth of a new cosmos with altered constants and forces. This might sound apocalyptic, but it also highlights the universe's dynamic nature. The same quantum fields that underpin matter's stability could, in principle, unmake it. The same expansion that allows galaxies to form could eventually tear them apart. The cosmos is not a static stage, but an evolving arena where creation and destruction dance in endless cycles. So what does this all mean for us? Every atom in your body participated in this cosmic saga. The carbon in your cells formed in stellar cores through nuclear fusion. The calcium in your bones originated in supernova explosions. The iron in your blood came from stars massive enough to fuse elements up to iron before collapsing. The gold in jewelry traces back to neutron star mergers. You are, quite literally, stardust, the product of cosmic forces operating over billions of years. Moreover, the same equations describing quark confinement, neutron star structure, black hole dynamics, and cosmic expansion govern the universe at every scale. There's a hidden unity connecting the infinitesimal and the infinite, the micro and the macro. Understanding one scale often illuminates another. Particle physics informs cosmology. Astrophysics tests quantum theories. The boundary between disciplines blurs when you realize that all phenomena emerge from a handful of fundamental forces and fields. Let me now fulfill the final promise, the secret tying these energies together. Physicists plot binding energies, explosion energies, gravitational potentials, and vacuum densities on logarithmic scales spanning 60 orders of magnitude. Remarkably, these data points form a nearly continuous hierarchy, suggesting that nature's extremes aren't random but follow a coherent pattern dictated by fundamental constants like the speed of light, Planck's constant, and the gravitational constant. This hierarchy hints at a deeper symmetry or principle waiting to be discovered, perhaps a theory of everything unifying quantum mechanics and general relativity. Imagine a future where such a theory exists. We'd understand not only how forces unify at high energies, but also why the universe inflated, what dark matter and dark energy are, and whether our vacuum is truly stable. We might predict the cosmos's ultimate fate with certainty: eternal expansion, cyclic rebirth, or sudden vacuum decay. We could even engineer technologies harnessing exotic physics, manipulating space-time, creating mini black holes for energy, or detecting gravitational waves with unprecedented precision. But until that day, we explore, observe, and theorize. Telescopes peer deeper into space and time, particle colliders probe higher energies, and gravitational wave observatories listen to the universe's whispers. Each discovery adds a piece to the cosmic puzzle, revealing connections that inspire awe and humility. Now, before we part ways, answer this: which force or phenomenon we covered today shook your understanding of reality the most? Was it the idea that quarks can never be isolated, no matter how hard you try? The realization that gamma-ray bursts outshine entire galaxies for seconds? The fact that neutron stars spin hundreds of times per second with magnetic fields strong enough to tear atoms apart from kilometers away? The notion that dark energy might one day rip apart atoms themselves? Or the chilling possibility that our vacuum could decay in an instant, erasing everything without warning? Drop your answer in the comments and challenge someone you know to watch this video. Ask them, did you know the same physics that binds quarks also drives the universe's expansion and could end it all? Let's spark a conversation, because the universe's mysteries are too grand to explore alone. And here's my final provocation. 90% of people live their entire lives without ever contemplating the cosmic forces that forged every atom in their bodies, the explosions that seeded the elements, or the dark energy shaping the universe's destiny. Are you content being part of that 90%? Or will you dig deeper, question more, and keep seeking answers? If you choose curiosity over complacency, hit that subscribe button, ring the notification bell, and join me on future journeys through the cosmos. There are more mysteries to unravel, more extremes to explore, and more connections to discover. Thank you for traveling with me across the universe's most powerful forces. From the strong nuclear bonds holding matter together to the dark energy tearing space apart, from the brightest explosions to the densest remnants, we've witnessed nature at its most extreme. Remember, you're made of stardust, governed by the same laws that sculpt galaxies and ignite stars. Carry that knowledge with you, share it, and never stop wondering. The universe is vast, strange, and beautiful, and understanding it is humanity's greatest adventure. Until next time, keep looking up.